All right, so I want to welcome everyone back. This is going to be our very first screencast for Chapter 2. At this point, you've got a little bit of experience under your belt about how these screencasts work. The first one we had done was Chapter 1, and I kind of combined two sections into that particular chapter, so it was a little bit longer than a normal screencast. Hopefully now, from this point forward, I'll be doing the screencast for the most part by section, so hopefully that's going to cut down on the time. So we've gone through scientific method. That was chapter 1, just to kind of get our feet wet, and like I had said, just to review a few things that hopefully you've learned in the past. And now what we're going to do is we're going to start in on the content that we're going to be learning in biology. And so the very first thing we need to touch on is the idea of the chemistry that occurs within the area of biology. And so chapter 2 is going to focus on organic chemistry. Some of the stuff we're going to look at in sections 2.1 and 2.2 probably are going to look a little bit familiar to you because you probably learned some of this stuff back in physical science. But some of the stuff we're going to look at in 2.3 and 2.4 when we start talking about the organic molecules, that stuff's going to be brand new. So a lot of the stuff we're going to talk about today is going to be relatively, probably for the most part, just review for you. So the very first thing we need to look at is the idea of an element. Now, if you think back to physical science, you probably talked about things like elements, molecules, and compounds, and we need to be able to distinguish between these. If you look here, it says all matter is made up of a limited number of elements. And when they say limited, they're referring to that periodic table of elements you were probably introduced to back in 8th grade. Now, the definition for an element is simply a pure substance that cannot be broken down by any type of chemical reaction. So it can't be broken down any further. It's absolutely pure. And down here towards the bottom, we have some examples of the elements that you would find on that periodic table of elements. Over here on the left, the S is going to stand for sulfur. So sulfur is going to be found in most cases in a solid form. Here it's kind of been crushed up in a powder form. Copper is a type of metal, so the symbols that we use to identify copper is Cu. Right here, this is going to be an example of carbon. This is an example of phosphorus. Down here towards the bottom, we have an example of sodium, which is a highly reactive metal. This is going to be magnesium, and over here on the far right is going to be an example of gold. Now what you're going to notice is sometimes the symbols that we use for certain elements are not going to quite match up with the name of the element itself. You know, gold, of course, and then we have Ag. So you kind of have to be aware of that as you kind of work with these different types of elements. Now, when you're talking about elements, of course, we need to break those elements down even further. In other words, they do have parts or components that make up those elements. So each element is made up of something called an atom. And atoms are simply the basic unit of all matter. And the word atom is going to come from the Greek word atomos, meaning unable to cut. Even though at this point we have been able to take certain atoms and actually break them down into their core components. Atoms are essentially made up of protons, they're made up of neutrons, and they're made up of electrons. And what you're going to find over here on the right is the protons and the neutrons essentially make up the core of the atom, and these things you see on the outside, these yellow spheres, these are going to be the electrons, and they tend to kind of rotate or revolve around that center core. The number of protons is going to determine what that element is. So it's going to give it its identifying factor. Whether it's carbon, whether it's phosphorus, or maybe it's magnesium, it's all based on those number of protons. Now, the properties of subatomic particles, there's a few things we need to be aware of when it comes down to each of those three particles. And so what we tend to look at, which basically makes them kind of unique, is their atomic mass and the charge that they actually carry. So if you're looking at a proton within an element, within that atom, typically the atomic mass for the proton is going to be atomic mass of 1. And an atomic mass is simply a unit of measurement. The charge that you would find on the proton is going to be a positive charge. For a neutron down here, it's going to have the same atomic mass as the proton, and it's actually not going to have no charge. I mean, it's not going to have a charge. It's going to be considered neutral. The electrons, which revolve around the center core, the protons and the neutrons, is going to have an atomic mass of 1/1840th of that one that you would find in a proton or a neutron. And the charge you would find on an electron is going to be a negative charge. So a positive charge on a proton, negative on an electron, and then of course a neutron is going to be considered neutral. Now occasionally what you're going to find is you're going to find some elements that kind of vary. In other words, it's the same element, but there are a few things that are different between those different versions of that element. What we do is we call those different versions of the same element isotopes. Now, it's an isotope because what happens here is they actually have the same number of protons, the same number of electrons, but the number of neutrons is going to be a little bit different. Some isotopes are considered radioactive because of that small change in the number of neutrons. And this means that they can actually self-destruct and give off a large amount of energy. So down here towards the bottom, you see different versions of carbon. So we have something called carbon-12, carbon-13, and carbon-14. Now, when you look at carbon-12, this is a very stable element, all right? So it's not really highly reactive. Carbon-13, a little bit different, again, from carbon-12 because of the difference in the number of neutrons, but again, relatively stable. But once you get to carbon-14, this is when it becomes radioactive and it can become dangerous. And so it becomes a very unstable type of element. So again, an isotope is simply a difference in the number of neutrons, and because of that, it kind of changes the characteristics of that particular element. As I had said earlier, when it comes down to how we actually organize these different elements, we usually use something called the periodic table of elements. And you can see this over here on the left. When you look at this periodic table of elements, you're going to see lots and lots of different versions of this table. But the things you need to be concerned with on this table are the atomic number, which typically is going to be right above the symbol for that element. It's going to identify the number of protons you would find for that element. The element symbol, so it's going to be one or two letters that represents that element. And again, sometimes the symbol that you would see may not match up exactly with the name for that element. Again, my example in the beginning was gold, but it has the symbol Ag. The element name typically is right below the symbol, and then we have the atomic mass. Now, mass essentially refers to weight. So this is the average weight of an atom. So we're looking at the protons and the neutrons. We usually don't consider the electrons because they don't really have a huge effect on the weight of that particular element. Now, when you think about something called a compound, it's going to be a little bit different when compared to either an element, an atom, or even a molecule. A compound is going to be a substance that is formed by the chemical combination of two or more elements in definite proportions. Now, a good example of a compound is going to be water, H2O, or salt. You know, typical table salt is going to be made up of two different elements. It's going to be made up of sodium, and it's going to be made up of chlorine. When you look at water, it's made up of hydrogen, and it's made up of a second element called oxygen. Usually, they're very different from the individual elements that form them, basically meaning that the characteristics you would find for each individual element are going to be very different as compared to the characteristics for the compound itself. A good example of that is salt. If you put sodium and chlorine together, it's a very safe, it's an edible type of compound. In other words, it's not going to harm you. But if you split these two elements apart and you look at them individually, sodium is a very reactive and dangerous type of metal, and chlorine, same thing. It's typically a gas, but it's very, very dangerous. And so, but when you bring them together, you get something relatively safe. So it can change their characteristics when you bring certain elements together. Now, when you bring those elements together, of course, we need to have a way to hold them together. And what we do is we look at the types of bonds that are being used to hold those elements together. So compounds are held together by chemical bonds. So the type of chemical bonds that we typically look at are ones called ionic, and the second would be covalent. Now, ionic bonds are going to form when atoms actually gain or lose electrons. And when they do that, they become a little bit different, and instead of calling them an atom or an element, we start to refer to them as ions. If you look over here on the right-hand side, what we're doing here is we're looking at a sodium atom and we're looking at a chlorine atom. So what's going to happen here is this particular electron, which typically is on the outside again of that nucleus, they're kind of floating around or revolving around that nucleus, it's going to be given to the chlorine. And so this area right here is going to be the bonding site. In other words, this is where this particular bonding occurs. And this is going to be an ionic bond in this case. So we have a sodium ion and we have a chloride ion because the sodium gave up an electron and the chlorine gained an electron. So this is going to be that relatively safe compound that we looked at earlier called sodium chloride or salt. Now, ionic bonds are going to form, as I had said, when you either gain or lose electrons. And when that happens, you have ions with opposite charges, and what that does is it actually causes an attraction, and that's what kind of brings these two elements together to form this compound. Now, the second type of bond I had said we would look at would be something called a covalent bond. Now, this is going to be a little bit different from ionic because in this case, the electrons are going to be shared between the two atoms. This is a bit stronger than ionic bonds, and what's a little bit different also when you compare them to ionic bonds is that the covalent bonds between two atoms could be a single bond, could be a double bond, or it actually could even be a triple bond. And the more bonds you have, of course, the stronger the connection between those two atoms. Now, molecules are structures that result when atoms are joined by covalent bonds. So whenever you use this type of bonding process, you can use the term molecules. Now, over here you can see we have the compound called methane, and it has one carbon and four hydrogens. Well, what's happening is the one atom that you find on that hydrogen is being shared with that carbon atom that you see in the middle. And so sharing is occurring between these four hydrogen and that carbon in the center. Another example of a molecule that actually has covalent bonds within its structure is the DNA molecule that you see down here towards the bottom. Now, when you're talking about those electrons, we sometimes give special names to certain electrons that surround that nucleus. We call certain electrons valence electrons, and these are important because what they do is those are the ones that actually participate in the bonding between two different atoms. And again, these valence electrons will occur on the outside. So if you look at sodium here, it has a proton number of 11. The number of neutrons in this case is going to be 12. And then if you look out here, we have various electrons that are floating around that nucleus. And if you notice, they compose basically what we call shells around that nucleus. So in the first orbital or shell, orbital is another name you could also use, you have 2. And then if you look in the next orbital or shell, you have 2, 4, 6, 8. And then if you notice on the very outside, we have one additional electron, and this is going to be called the valence electron. And again, this is going to be the one that's available for bonding with another atom. Now, when you look at valence electrons, most atoms are going to be stable when their valence shell is filled. And what that means is, if you look here, carbon is relatively stable because as it bonds with these hydrogen, the entire shell is filled. And typically, the maximum number of electrons you can have in a shell is normally going to be 8. So this entire shell is filled. Hydrogen can only hold 2 electrons in its valence shell. All other atoms can hold 8. So there is one exception to that 8 number that I just mentioned. Hydrogen, the number of valence electrons is 1. The number of electrons needed would be 1 to fill the shell. If it's carbon, they have 4 on the outside, and you can only add 4. In other words, there are 4 possible bonding sites to fill up that shell. And you can see nitrogen has 5, so there's only 3 electrons that would be needed to fill up that shell. So again, that number needs to add up to 8 to make it relatively stable and to fill that shell up. All right, so that's going to finish up our first screencast for Chapter 2. And so again, this is Section 2.1. And as you had done with Chapter 1, please make sure that you have your screencast notes completed before you come to class.